Okay, so today I am going to present another problem from this recent CSIR NET July 2024 exam, and the problem is from classical mechanics. So let's look at this problem. So this is the diagram given in the question. You can see there is three string, each of length L, two springs, spring constant K, and three mass M. This is the initial configuration. And after displaced, they have given that these are the normal mode frequencies, that is root under G by L, root under G by L plus K by M, and root under G by L plus 3K by M. So these normal mode frequencies are given, and now you have to find that what are the normal mode displacements actually. So the AI is actually, so here three normal mode frequencies are given. So there are three kind of displacements, A1, A2, and A3. So this is the equation to find the normal modes, that is Vij minus omega squared Tij. This is a matrix, and Aj is a column matrix. This product of these two matrix should be equal to the null matrix, and this Aj will give you the normal modes. Okay, so this is actually a straightforward problem. If you can solve it in exam hall, it is a doable problem in exam time also. So okay, this is the kinetic energy first. Kinetic energy is ml square theta 1 dot square plus theta 2 dot square plus theta 3 dot square, where you have this kind of displacements. Angular displacement of the first mass is theta 1, second mass is theta 2, and third mass is theta 3. So here in this problem you can only have angular displacement because this length of the strings are constant of the problem. So you can only have angular displacements. So okay, this is kinetic energy, and it is actually straightforward. The potential energy is a little bit complicated. So what are the potential energies? So the first spring have some kind of contraction or extension. So there is half k delta x1 2 square. So this is the first mass, the mass 1, and this is the mass 2, and these two go through displacement, angular displacements theta 1 and theta 2. So this is the extension delta x1 2 square. And for the second spring it is similar, k by 2 delta x2 3 square minus mgl cos theta 1 cos theta 2 cos theta 3. This is the potential energy due to the gravitational acceleration. So if you think this is your reference point, the point of suspension is your reference point, then the gravitational potential energy of these three masses is minus mgl cos theta 1 minus mgl cos theta 2 for mass 2, and minus mgl cos theta 3 for mass 3. So these two are the spring potential energy, and the last three term are the gravitational potential energy. So for mole theta, we can do this approximation. Cos theta is 1 minus theta squared by 2. So I will use this substitution in terms of cos theta. And for delta x12, what is delta x12? See, the first spring have gone through first extension L theta 1. L theta 1 is the arc length when you displace it by angular displacement theta 1, and then it have another contraction, that is L theta 2. L theta 2 is the arc length. So overall it has its change of length actually L theta 1 minus L theta 2, where L theta 1 is arc length and L theta 2 is also the arc length. So this is the change of length of the first spring, and similarly the change of length of the second spring is L theta 2 minus L theta 3, the arc lengths, the change of arc lengths actually. Okay, so now our potential energy is already ready, the expression of potential energy. You can combine the terms of theta 1 square, theta 2 square, theta 3 square, theta 1, theta 2, theta 2, theta 3, and there is no cross term of theta 1 and theta 3. Okay, so this is the total potential energy. Now you can find the matrix of Vij. The Vij is del to V del xi del xj. So for example, V23 is del to V del theta 2 del theta 3 for this problem, because thetas are the generalized coordinates for your problem. So you can write the matrix of V by going through this process del to V del xi del xj. So this is the first term, where del to V del theta 1 square. This is the second term, del to V del theta 1 del theta 2, and similarly the other terms. So this is the matrix for potential energy. Now this is your first omega. Your omega 1 is root under G by L. So you have to use now this equation Vij minus omega square Tij into Aj is equal to 0. And what is your Tij? The matrix T is omega square into the matrix of ml square in the diagonal, because your kinetic energy of expression ml square by 2 theta 1 dot square plus theta 2 dot square plus theta 3 dot square. So the matrix, the kinetic energy matrix is diagonal matrix and it is a simple matrix. So now we substitute Vij minus omega square Tij, and in place of omega square we substitute root under G by L. So this is the first term KL square plus MGL minus omega square. In place of omega square I have G by L, and this is the first diagonal element of Tij. This is ML square, and this is the second diagonal element. Similarly, in place of omega square I substitute G by L, and the ml square is the second diagonal term here, and similarly the third diagonal term, and the off diagonal terms are not changed because Tij is a diagonal matrix, and there is multiplied by the column matrix of Ai, and this is a totally a null matrix. So now this you have product of two matrix and that is a null matrix. So you solve this kind of problem multiple times in quantum mechanics. So you can simply uh, find the relations between A1, A2 and A3, and if you do that you can find that A1 is equal to A2, A2 is equal to A3, and for this case A1 is equal to A2 is equal to A3. So you can say that your normal mode will be 111. So both the masses will displace equally in same direction. Okay, so now try another, for another omega. Here omega square is G by L plus 3k by m. The technique is similar in terms of omega square. In the place of omega square you have to substitute G by L plus 3k by m, and the diagonal elements are ml square. So this is first diagonal terms, this is second diagonal term, and this is third diagonal term, and other terms remain same, and again multiplied by the column matrix of AIs, and this is total a null matrix. Okay, so this is now the product of matrix, and this is a null matrix. So you can find the relation between AIs. So two, for this case 2A1 is equal to minus A2, and 2A3 is equal to also minus A2, and if you combine these two then you can get A1 plus A2 plus A3 is equal to 0. So you can choose A1 is equal to 1. If you choose A1 is equal to 1, then A2 will be automatically minus 2. And when A2 is automatically minus 2, A3 will be automatically 1. So by choosing any one, you can also choose A1 is equal to 2, and accordingly other elements will get changed. So okay, this is the another normal mode. And similarly for the second another case, the root under G by L plus K by M case, you can find this is 1 0 minus 1. I am not doing this again. So for this case the third option is the correct option. Yeah, so it is actually a straightforward problem. You can solve it in exam hall. Just to You have just to be a little patient to solve all the eigenvalues. Okay, so thank you. Any comments are welcome.